Hi class, this is Sir Alex Basco and welcome to our lesson in General Physics 2. Today we are going to finish lesson 7, Gauss's law. We are going to talk about today the two remaining symmetries, cylindrical symmetries and planar symmetries. So previously what we've discussed is all about spheres and spherical symmetry, where we create a Gaussian surface or an imaginary sphere surface in order for us to find the electric field at a certain point from the center of a sphere, either when you're dealing with a conducting sphere or an insulating sphere. So this time let's discuss these two symmetries, cylindrical and planar, and where we use these symmetries when we want to find the electric field. Let's begin with cylindrical symmetry. Cylindrical symmetry is a Gaussian surface that we create if we want to find a certain electric field on a long wire. So what do we mean by that? So for example, you have this long wire, or this infinitely long wire, and if you think of a long wire, you may think of this as line of charges, or what you can think of is something like this. So infinite long line of charges, and this infinite charges has a charge symmetry that we are going to call the linear, or charge density that we are going to call the linear charge density. And this actually makes sense, and we use lambda, this is the sign for lambda, in order to find the linear charge density. Linear because it is a line, and the unit for a linear charge density is basically coulombs per meter. So what we are doing here, if we want to find the density of a portion of these wire, we have to solve for the linear charge density, that is a certain coulombs per meter of the wire. So you may want to call this your lambda, and then you may want to ask, what is the electric field E at some point at distance R from the line? So for example, you choose this part of your wire and you want to find out the electric field at this point. What is the electric field at this point if you have a long wire? In order for you to solve this type of situation, what you have to do is create a Gaussian surface. Remember what a Gaussian surface is. A Gaussian surface will help you identify the electric field, and also this electric field is, or this Gaussian surface has to have a symmetry. So how can we create a shape that can help us create this Gaussian surface? The answer to that is a cylinder. Since this is a long sphere of wire, the electric field that is passing from this line of wire is basically going in every direction to its side, correct? So what you want to do is, if you want to find an electric field at a certain distance from this line of wire, you have to enclose this line of wire, or this line of charges, in a cylinder. And you have to imagine that this line right here, this line of charges, is strictly in the middle of the cylinder. So from there, I hope you can imagine how it creates a symmetry. Okay, and then what we are going to do next is, you can now imagine your electric field. Your electric field is passing from this line of wire, and they're going up and they're going down, and they're actually also going backwards and going in front of you. So imagine that it's a 360 electric field, and all of them, if you can imagine, is passing through the cylinder. This electric field is passing through a cylinder. So let's take this. Now, having said this, remember this green cylinder here is your Gaussian surface. It's your fake, or not fake, your imaginary surface that you have to create in order for you to solve this electric field. So the electric field of this line of charges is pointing to the walls but not at the end caps. So if this is your cylinder right here, and this is the electric field from this line of charges. And if you notice, like I mentioned, the electric field is in a 360 degree, it's happening throughout the 360 degrees. And what that tells you is that the electric field is happening at the walls at your cylinder. So the electric flux is happening on the walls of your cylinder. So if we want to measure the electric flux, that is basically electric flux and then the integral sum of the magnitude of the electric field multiplied by the differential of an area. So if we have this walls of cylinder and we solve for the electric flux at very infinitesimally small part of the walls of cylinder, you would get that the electric flux is basically Q total divided by epsilon naught. And using this equation, we can derive that EA is equals to Q total divided by epsilon naught. And from this equation, we can now derive the equation for the electric field. If we want to measure the electric field at this point, we can now use this equation. How are we going to do that? So first, we have to divide both sides by A. That's what we did here. And now we have to find the area of the cylinder. So what is an area of the cylinder? But first, take note that the electric flux is only happening at the walls. It's not happening on the end caps. So the area that you are looking for is actually not the area of the whole cylinder, but only the walls of cylinder. So if I take my cylinder and cut it open, if you notice, if you cut the cylinder open without end caps, wala siyang, there's nothing at the top or the bottom, you may notice that you have something like a rectangle or a square. And what is an area of a rectangle or a square? We know that an area of a rectangle of a square is equals to length times width, right? So if I take this as my length, this is my length because this tells me the length of my cylinder. So what are these areas right here? So what is this one? So this red circle right here, if I open, it's basically this one right here. So what is this? As you can see, this is will look like a circle, right? So this is actually your L. This width right here is actually equal to 2 pi r. So if I want to take the area of this opened cylinder, the area would be length, which is that one, multiplied by width, which is equals to 2 pi r. So A is equals to 2 pi r. That is the area for your cylinder. After looking for the area of the cylinder, just substitute that value. You will have the electric flux at this point is equals to the total charge of the divided by epsilon naught, or the permittivity of free space, 2 pi r L. And then what you want to do now is you want to substitute your Q total with your linear charge density. This is necessary because this Q total right here is the total of the whole total of the whole line of wire, this whole blue thing here. And we know that this is infinitely large, but we are only what we are only looking for is the electric flux here, and more specifically this length right here, this limited length. So I want to find the total charge of this limited length, and in order for me to do that, I have to use my lambda. Lambda is the linear charge density, how much charge per millimeter is available in this line. And the equation for that is lambda is equals to the total charge of the line divided by how long is your wire, right? So if I have 10 centimeters or 10 meters of wire, and the total is, I have a total of 50 columns, so that's just 50 divided by 5 or 10 centimeters, and that would give me about 0.5 columns per meter. And then why is this necessary then? We have to substitute the Q total with this Q right here. So rearranging the equation, you would get Q is equals to lambda multiplied by the length. So substitute that value, you would get E total is equals to lambda multiplied by the length divided by the permittivity of free space epsilon naught 2 pi r L. So you can use these two equations. You use this equation for limited length, right? If you know the charge if you know the charge per meter, and you use this equation if you're looking for the electric field for the whole basically for the whole line. Okay, so those are the two equations that you have to use for cylindrical symmetry. And then you just have to cancel that because the length get cancelled. So you are left with E is equals to lambda divided by 2 pi r epsilon naught. So those are your two equations. So let's have this sample problem, but let's move on to our right here. Okay. So an imaginary cylinder with a radius 0.35 meters. So this is my cylinder right here. It has a radius of 0.35 meters and length 1.5 meters. So the length of my cylinder is 1.5 meter. Has an infinite line of charge with a linear charge or with a linear density of 75 nanocoulombs per meter. So I have this infinitely long line of charges, this blue line right here. And the charge density, or meaning the coulombs per meter, how much coulomb is available per meter of this line, is 75 nanocoulombs. First, what is the total charge enclosed by the Gaussian cylinder? B, what is the electric flux through the cylinder to the infinite line of charges? And C, calculate the electric field at a point 3 meters away from the infinite line of charges. So let's solve this. Let's write our given first. Let me just move this. Okay. So our first given is we have an imaginary surface and the radius of our surface is 0.35 meters. And the length of our cylinder is 1.5 meters. And then they also gave us our linear charge density, which is our lambda, is equals to 75 nanocoulombs per meter, or that is equivalent to 75 times 10 raised to negative 9 coulombs per meter. And let's write what is being asked. It's asking what is the total charge enclosed by the Gaussian cylinder. So how much is the total charge? Q total enclosed by this cylinder. Next, it's asking us what is the electric flux through the cylinder through the infinite line of charges. So what is the electric flux? I'm not sure, it's not writing. So what is the electric flux through the cylinder due to the let's write cylinder, electric flux through to the Gaussian cylinder. And lastly, it's asking what is the electric field 3 meters. So if I have this and if I measure this distance of 3 meters, what is my electric flux here? That's basically what it's asking. Okay, so the formula that we have to use, I'm not sure why it's not writing properly. Okay, so let's just write our formula here. I don't know why I can't write it this area. So the formula that we have is, first, if we want to find the Q total, and we have our lambda, the equation, Q is equals to lambda times length. This came from the equation of our linear charge density, which is lambda Q divided by length. We just got that, just rearrange the equation. And then the other equation that we have is for the electric flux. The electric flux is equals to Q total, or the total of all the line charges divided by the permittivity of free space. And lastly, the electric field at a certain distance can be measured if we are given the lambda as lambda divided by 2 pi r epsilon naught. So let's write our solution. So the first problem that we have, if you are looking for the Q total, so meaning the total charge of the infinite line, what is the total charge enclosed by the Gaussian surface? So if we have to find that, let's first solve or find the Q total, and that is equal to, if we have to find the total charge enclosed by the Gaussian surface, so what we are looking for is basically just the charge within this limited length of the Gaussian cylinder. So how much charge is available per this length? And we know that we already know the linear charge density. Linear charge density basically tells us how much charge is available per meter. So in order for you just to find how much Q total is, or Q is available within this limited length of your Gaussian surface, you just have to use this equation. So you know that lambda is equals to Q divided by length. This tells you your charge density. So if you want to find how much Q you have at a certain length of your cylinder, just substitute this value right here and you would get this. Let me move that here. So that's Q is equals to lambda over L, and that is equals to, that is equals to 75 times 10 raised to negative 9 coulombs per meter, multiplied by the length of your cylinder, which is 1.5 meters. So the meters gets cancelled and you are left with 1.25 times 10 raised to negative 7 coulombs. So that's how much charge is available that is enclosed in your Gaussian surface. That is the Q total found inside your Gaussian surface. And then next question is, what is the electric flux through the cylinder due to the infinite line of charge? So the next part is what is the electric flux through the cylinder? So meaning how much electric flux is happening through our cylinder. And this is easier because we now know how much charge is available inside our cylinder. So in order for us to find this, what we just have to do is use the equation Q total, or flux is equals to Q total divided by epsilon naught. And the Q total here is the total charge found inside our cylinder, which is 1.125 times 10 raised to negative 7 coulombs, divided by the permittivity of free space, which is 8.8542 times 10 raised to negative 12, and that is coulomb squared per Newton meter squared. And the answer is about 12,700 newtons. So that's 12,712 Newton meter squared per coulomb. So that's how much total, that's how much electric flux is happening on your cylinder. And lastly, calculate the electric field at a point 3 meters away from the infinite line of charge. So we know that there is an electric flux happening in this cylinder. So if I choose a point that is 3 meters away, so this is my point from the point from the infinite line of charge, what is the electric field at this point? So we've discussed how we can measure that. We've derived the equation. We know that if we want to measure the electric field at a certain point, at a certain distance, we just have to take the linear charge density divided by 2 pi r epsilon naught. So you have to calculate that. So we know our lambda. Our lambda is this right here. So this is our lambda, 75 times 10 raised to negative 9 coulombs per meter divided by 2 multiplied by pi multiplied by our radius. Our radius is, in this situation, you have to be aware, it should be 3 meters. Why is it 3 meters? Why not 0.35 radius? Well, you are looking at the electric field 3 centimeters. So what that means is you basically have to create another cylinder with a radius. So you have to create another Gaussian surface. So this is your fake Gaussian surface. So by creating that fake Gaussian surface, you can measure the electric field at this point. So that's 3 meters multiplied by permittivity of free space, 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. And that's how you can solve for your answer. And that is actually equals to 750 or 450 newtons per coulomb. Okay, so I hope it's clear. If you guys have any question po regarding this, do not hesitate to message me po. Okay, so this is only for cylinder. So if we have, or this is for cylinder symmetry, and again we use this if we have an infinite long line of charges. So if we have an infinite line of charges, so for example you have this various positive, this can be negative too, right? If you have this various charges, and if you want to find the electric field at a certain point with this distance right here, then you have to do is to create a Gaussian surface, a fake or an imaginary surface that will enclose all your charges. So this basically extends throughout, and that will tell, using this equation, then it will tell you how much electric field is available at a certain distance from that line of charges. That's basically what where we use this Gaussian surface or this cylindrical symmetry. Now let's move on to our last symmetry. Here. Okay, which is what we call a planar symmetry. Planar symmetry is when we want to solve for the electric field for infinitely large charge sheets. So imagine an infinite large horizontal plate with a uniform charge density sigma. So I just draw this. It looks small, but think of this as very massive, as a very, very, very long charged sheet. And if it is charged, if I can find the charge density sigma for this surface, right? So Since this is basically just a surface, yeah, since this is just a surface, all the charges are found on the surface, I can use sigma to find this, to find how much charge is available per square meter. So that is charge per square meter. This is not an area, it's just a flat sheet. So that is a surface. So we use charge density. So that is Q divided by area. What is the electric field at the surrounding area at distance r? So if I have this infinitely large sheet and I want to find the electric field at this point, at an area with a distance r, so this time I want to find the E here, and I have a distance r. In order for me to do that, I have to create another type of symmetry, and that symmetry, called the planar symmetry, it looks like a cylinder. So what I'm going to do is I'm going to create a cylinder that will encapsulate this area right here, and this cylinder bisects, so it goes through that infinite charge. And interestingly, the distance above this should be equal also to the distance there. So this distance right here is basically the top portion of the cylinder, and at the distance right here, it is equal to the distance above, and it also reaches at the bottom of the cylinder. So basically you have two halves of one cylinder being cut by your flat sheet. And then you would notice that since this is your charged area, electric field would go upward and would go downward. So basically what is happening here is what is also happening here, right? Okay, so one thing that in order to create this, there's three things that must be met. One, the end caps must be parallel to the surface. What are the end caps? The end caps is this right here. This is your end cap, and this end cap should be parallel to your surface, right? And another thing, the walls of your planar symmetry, which in this case cylinder, is perpendicular to your surface. So the walls are perpendicular. The end caps, this end cap right here and this end cap right here, are all parallel to the surface. They're 0 degrees or 180 degrees. And the distance above, which terminates at the end cap, and the distance below must be equal. So what you're left is, if I look at this sheet as a flat, so this is my sheet right here, and then my cylinder looks something like this, where the distance r and the distance r there are equal, and these two right here is perpendicular to the surface, and these end caps right here are parallel to the surface. So that's the symmetry you have to create, and from here I hope you can see that this is symmetrical, and this is necessary if you want to find the electric field at the distance r if you have an infinitely large sheet. Okay, now let's try this one. What is the electric field at the distance r? We know that the electric field, in order for us to find that, we have to understand that there is electric flux happening. We've used this equation. Electric flux is happening basically at the end cap. So if you can see here, this is your electric field right here, and they're all passing through the end caps, right? So there is an electric flux happening, which is the integral of the magnitude of the electric field multiplied by the differential of area. Only this time the differential of area is on the end caps and not on the walls. There is no electric flux happening on the walls, and this is equals to Q total divided by epsilon naught. And then we have to substitute the Q total, so this is equals to EA in the end. So substitute the Q total with our surface charge yeah, surface charge density. Surface because we're dealing with a flat surface. So it's QA divided by A, and we're left with Q is equals to sigma multiplied by A. And so this sigma right here is a measure of how much coulombs or electric charge is available per meter squared. And then just substitute that value, you would get Q total flux is equals to, we just changed that, no, this is equals to EA. Flux is equals to epsilon or sigma multiplied by the area of your surface, or area divided by epsilon naught. And the total electric flux consists of two end cups. So the electric flux at the top portion, so remember, if this is our surface and this is our cylinder, which has the same length, they have the same length, equal length, the electric flux happening, there is no electric flux at the side. All the electric flux are happening at the end cups, right? So we have our electric flux at the top and we have our electric flux at the bottom. So the total electric flux is equals to electric flux at the top and electric flux at the bottom, and that is equals to EA top and EA bottom. And so that's, and since these are just two equal same cylinder, so the area of the end cups are basically the same, and the magnitude that is passing them is also the same, so we can just mix the two. So you would end up having electric flux is equals to 2EA. So 2EA is equals to, right here, sigma multiplied by the area divided by epsilon naught. So if I am going to measure the electric field, I'll just have to divide both sides by 2 area. So divided by 2 area divided by 2 area, and what happens, the area get cancelled and you are left with this equation right here. The electric field at a certain distance is just basically equal to the surface charge density divided by 2 permittivity, 2 times the permittivity of free space. So this is the equation that you have to use to find the electric field at a certain distance r. Okay, I hope you guys are clear. But before we go to a sample problem, let's look at this. What happens if we have two infinitely charged sheets with opposite charge situated parallel to each other? So we have an infinitely large sheet that has a positive charge and another sheet that has a negative charge, and they're parallel to each other. What will happen? So they are situated at the distance r, right? So if you look at the positive charge, we know that the electric field, since this is positive, will be radially outward. And the electric flux, if you're going to measure this, are all equal to sigma divided by 2 epsilon naught. So the total electric flux happening here, or the electric field at this happening at this portion, is equals to the electric field happening in this portion, and if it passes the negative charge, that is also equal to the electric, that is still equal to sigma divided by 2 epsilon naught. The same thing is true for negative sign. For negative signs, since this is negative charge, the direction of the electric field is radially inward. It goes towards the negative sign. And the magnitude of this electric field are all equal. So they're all sigma divided by 2 epsilon naught. So when it's the electric field passes through the positive, and from positive to the negative, and from the bottom area of the negative. And what you notice, if you want to solve for the electric field in this type of situation, the electric field for a charge sheet that are situated parallel to each other and they have opposite sign, the electric field at the top portion area, if you notice, this is basically positive and this is negative, right? So what happens is you would cancel these two, the same thing this situation. So the only electric field available for a parallel charge sheet is the one that is found in the middle. And that makes sense because the direction of the electric field inside or in between these two is going in the same direction. So they're both going from the positive to the negative. So it starts from the positive and the negative. So the electric field, when you have two oppositely charged infinite sheets situated parallel, there is no electric field happening at the top and the on the top and the bottom. All the electric field is happening in the middle, and that is equals to sigma divided by epsilon naught. Okay, so we have this equation now. Electric field is equals to sigma divided by epsilon naught. The electric field is 0 outside the plates, but is equals to sigma divided by epsilon naught, or permittivity of free space inside the plates. The electric field points away from the positive and towards the negative plate. So it's just something like that. Now let's try and solve these sample problems. What is the electric field produced by infinite sheet of charge that contains a surface charge density of 60 nanocoulombs per meter? So if I have an infinitely charged sheet, so I'm just gonna try it that way because it's it's difficult to draw something so massive. And we know that the charge density, or how much surface charge density, this should be per square. Yeah, this should be per square because this is surface. So what is the electric field produced by an infinite sheet of charge that contains a surface charge density of, so we have a sigma of 60 nanocoulombs, and all of these are positive. So there is an electric field happening, going up and going down, right? So they gave us the sigma is equals to 60 nanocoulombs per meter squared. That is equals to 60 times 10 raised to negative 9 coulombs per meter squared. So what is asking is how much the electric field does this do? And if you notice, you don't have a distance. Why is that? Well, if you look at your formula, the formula for this is the electric field is equals to sigma to epsilon naught. If you notice, you don't have distance. What that means is if you have an infinitely charged sheet, the electric field is basically equal everywhere. So it doesn't matter if you're looking for the electric field at this point or the electric field at this point at higher, the electric field would theoretically going to be the same because your formula does not account or does not measure for the length or does not measure for the distance. So this is much easier to solve. So if I'm going to solve for this, I'll just have to plug in my number. E is equals to sigma to epsilon naught, that is equals to 60 times 10 raised to negative 9 coulombs per square meter divided by 2 times 8.8542 times 10 raised to negative 12 coulombs squared per Newton meter squared. That is equal to 300 or 3,300 390 newtons per coulomb. So that is the electric field due to this infinitely charged, this massive charge plate. And as you can see, the distance of where you want to find the E does not matter, because the the formula that we derive does not care about the distance. So this is much easier to find. I hope that is clear. Before we go, let's try to solve this last one. What is the electric field produced between two oppositely charged sheets with a surface charge density of 15 microcoulombs per meter squared? So we know earlier, if we have a charged sheet and they're parallel, negative, you have your positive, we know that the electric field is going towards this direction now, right? We just discussed this, and they gave you the sigma is equals to 15 microcoulombs per meter squared. That is equals to 15 times 10 raised to negative 6 coulombs per meter squared. And then the formula or I forgot they asked. It's asking for the electric field between. So the electric field between, and we know that's only found between, because if you have positive and negative sheets that are situated parallel, there is no electric field here. There is also no electric field at the top or the bottom. So the electric field is only found inside or in between. The formula for that is electric field is equals to sigma divided by epsilon naught. So solution, E is equals to 15 times 10 raised to negative 6 coulombs per meter squared divided by 8.8542 times 10 raised to negative 12 coulombs squared per Newton meter squared. So the electric field in between these two charges is equal to 1.69 times 10 raised to negative raised to 6 newtons per coulomb. So that is the electric field happening in between these two charged sheets. Okay, so that is all about Gauss's law and Gaussian surface. If you guys have any question, do not hesitate to message. Thank you so much, guys, and may you guys have a great day. Thank you so much.